Hello class, in this video we are going to look at similar triangles. In the previous video we looked at just similar figures in general. Now we're going to be looking specifically at triangles. Alright, so let's take a look at some stuff. Now first, we said that similar figures were a dilation of each other. So I'm just going to dilate this down, keep the aspect ratio the same, and there it is. Similar triangles. Same thing over here. I'm going to use the rectangle, dilate that down. There you go. Now, with quadrilaterals or anything that has more than three sides, we noticed that the angles have to match up, the sides have to be proportional, and we've got to check all of that, right? Because I could come over here and I could just stretch out one side here, and my angles are still congruent, but my sides are no longer proportional, because this side's almost the same and that one's only about half, right? Sides aren't proportional. Well, with a triangle, can I do that? If I take it and I just stretch out one side, well, that changed my angles, didn't it? My angles aren't the same anymore, so that's an issue. So I can't just stretch out one side and keep my angles the same. If you stretch out anything and you don't keep your aspect ratio the same, it's not a pure dilation, then your angles change, and that's no good. All right? So there's that. Also, remember with quadrilaterals, we saw, especially with squares and rhombi, that I could just knock the thing over. Right? My sides are still the same length, but the angles have changed. And so you've got to check the side lengths, just having the sides the same or proportional, because I could just take that and shrink it down. Okay, it's proportional. All the sides are proportional, but the angles are different, right? Well, with triangles, is that possible? Can I take it and lean it over without changing the sides? And no, you can't. Remember, the side-side-side congruence theorem says if the sides are the sides are all the same length, then those angles automatically match up as well with a triangle. Not with quadrilaterals or pentagons or anything like that, but with triangles, if you have three sides and you don't change the sides, then the angles can't change either. Okay, so with quadrilaterals, I could keep the sides the same and change the angles, but with triangles, you can't. So what that means is that as long as those angles are the same, the sides are automatically going to be proportional. It also means as long as the sides are proportional, the angles are automatically going to be congruent. So for triangles only, having congruent angles or proportional sides is enough to prove similarity. You don't need both. If you have more than three sides, you got to have both. You got to have congruent angles and proportional sides. But with a triangle, one or the other is good enough. So we do have some triangle similarity theorems here. Let's take a look at these. First one, AA similarity, angle-angle similarity. If two angles of one triangle are congruent to two angles of another triangle, the triangles are similar. So for example, my two triangles down here right now, I don't know, look good, but we can't tell. But if I do this, and so these two angles are congruent to those two angles, the triangles are going to be similar. I don't actually have to have the third. Why don't I need the third? Well, because all three angles add up to 180, and so if these two are congruent to those two, that third angle has to be the same measure to make it all add up to 180, right? So as long as you got two angles, that's good enough, because the third one's automatically going to work, and if all three angles work, then the sides are automatically going to be proportional. Okay, so that's angle-angle similarity. The next one we're going to look at is side-side-side similarity. Do make sure you specify that this is side-side-side similarity. Don't just put SSS, so that's going to be, people are going to think you're talking side-side-side congruence, right? So, side-side-side similarity. If all three sides of one triangle are proportional to the corresponding sides of another triangle, the triangles are similar. So, for example, here, 3, 4, 6, 6, 8, 12. Notice the sides all doubled, so they're all proportional. Okay, I don't have to check the angles. As long as the sides are proportional, angles are automatically going to be congruent in a triangle. So it's good, saves us some time. And the last one, if two sides of a triangle are proportional to the corresponding sides of another triangle, and the included angles are congruent, the triangles are similar. So that would be something like this. So I've got two sides here, 5 and 4, are proportional to their corresponding sides, 15 and 12. Right? See, both are multiplied by 3. And that included angle, the angle in between them, those angles are congruent. So SAS similarity. Again, you're going to have to specify that this is the similarity theorem, not the congruence theorem. Because if you just put SAS, it's going to be assumed that you're talking about the congruence theorem. All right. So here it is. If we just have this little bit, I know that these two sides are proportional. I know those angles are congruent. I don't even have to check the other sides. I know they are automatically going to be good. All right. So shortcuts for triangles, because triangles are cool that way. A lot of triangles stuff we get shortcuts for. So what can we do here? All right. So let's take a look at this. I have a triangle, and I've got a parallel line in the middle of the triangle. Okay, this probably not a mid-segment. Doesn't look like it. Anyways, now a couple of things. If I've got this parallel line, what does that mean? Well, that means I've got corresponding angles, right? Corresponding angles are congruent to each other. So this angle is congruent to that angle, this angle is congruent to that angle, and oh, look at that. I now have angle-angle similarity. I know that the big triangle is going to be similar to the small triangle. So I can write a similarity statement here, and there we go. Triangle ACD is similar, remember that little squiggle there, that means similar to ABE. You got to keep them in order. A in this triangle goes with A to that triangle. C in the big triangle is corresponding to B in the little triangle, and D matches up with E. All right, so they all match up. Got to keep them in the same order. So if those are similar, what does that mean about the sides? It means they're proportional. So let's go throw some sides in here, and let's take a look at this. All right. So I know that AE has a length of 4, AB has a length of 3, and the entirety of side AC has a length of 12. Real quickly, let's just find the length of AD right there. So we're going to set this up in a proportion, which hopefully you remember how to solve these. All right? So 4 to something, I don't know, is equal to AB over AC, so 3 to 12, right? 4 over AD equals 3 over 12, and we're going to solve this using the cross products, right? Little butterfly method. So 3 times whatever AD is equals 4 times 12, so 4 times 12 is 48, and then we're just going to multiply that out. Divide both sides by 3, and AD equals 16, so that's 16. Easy peasy, right? Not a big deal. But let's look at something else. So let's look at these other two segments down here, ED and BC. All right, so 16 minus 4 is 12. 12 minus 3 is 9. So this is 12, that's 9. And I want to point out something here. If I take these two segments, these two pieces of the side, not the entire side, just the pieces of the side, and set those into a proportion, well, that would be 4 over 12 equals 3 over 9. And checking the cross products, that works, doesn't it? 4 over 12, 3 over 9, so 4 times 9 is 36. 3 times 12 is also 36. So my proportion checks out, right? Another way you could do this is you could simplify both of them. Those are both equal 1/3. So you have equivalent ratios. So what this says is that if you've got this parallel line inside of triangle, it's going to divide those two sides proportionally. This is called the triangle proportionality theorem, also called the side splitter theorem, because it splits the side with a parallel line. Right? If a line is parallel to one side of a triangle intersects the other two sides of a triangle, then it divides those two sides proportionally. So it divides these two sides here into a proportion, right? Because it's basically just two similar triangles, isn't it? All right, and let's see here. So once again, triangles are special. They get shortcuts. You don't have to check all the sides and all the angles in order for them to work. As long as you have either just two angles that are congruent, which would be like that, two angles that are congruent, or all three sides are proportional, or two sides and that included angle, then you're good. You do not have to check everything. And that is for triangles only. Quadrilaterals, stuff like that, you still have to have, you're going to have to check all of the sides for proportionality, all of the angles for congruence. But for triangles, we have shortcuts. So that's nice. And remember, if you have a parallel line that goes through two sides of a triangle, it's going to give you a smaller, divide that out into similar triangles, and the sides are going to be divided up proportionally. Hope you found that useful, and I will see you in the next video.